Going to look at kind of a general first order linear equation. I haven't even defined what a linear equation is yet, though I have been using that term. And so we're going to do some of that now and look at even a more we'll look at a different example than that we've seen, a different type of example. Okay, so basically at the end of this section, what I want you to be able to do is use the method of characteristics. So that's the sort of main takeaway here, is to use the method of characteristics. So a general first order linear equation is an equation in the following form. You've got some known function, a of xy, a of xy, whoopsies, a of xy times the partial derivative of u with respect to x plus b of xy times the partial derivative, that's an x, not a y, times the partial derivative of u with respect to y is equal to another function, c of xy times u plus another function, d of xy. Okay, so here a, b, c, and d are all known functions, are all given functions. So a, b, c, d are all known functions, or I should say given functions. These are all given functions. Okay, a, b, c, and d are all given functions, and u is unknown. And we're trying to solve for u. We're trying to use this information, this equation that relates u and its derivatives, to figure out what u is, or figure out some information about u. Now, why do we call this linear? Well, we call this linear because it is linear in the function u. So in other words, if why is it linear? I'll basically say it this way: it's linear because if u1 and u2 are solutions, then so is any linear combination of u1 and u2. So then so is gamma u1 plus lambda u2 for two real numbers. So for gamma and lambda in the real numbers. Okay, so it's linear in the u. It's linear. We say this is linear in u, which is what the blue statement there means. Okay, so the vector a of xy, b of xy. So in all of the previous problems, a of xy, b of xy, these have been constants, 2 and 3, 1 and minus 1, whatever it was. But in general, they can depend on the x and y, on the x and y value. This is called the characteristic now I don't know how to spell, characteristic direction of the PDE. Okay, and so what we get, just like in the previous examples, we're going to get a system of differential equations. So x dot of s is always going to be the thing that's multiplying the partial derivative of u with respect to x. So this is a of xy, and we'll pick some initial condition x naught. Y of s is going to be b of xy, and we'll pick some condition y naught. And this is chosen so that it is chosen to be on the Cauchy curve. There's no Cauchy data given here yet, but this is, if there is, this is chosen to be on the Cauchy curve. And now, what is z of s? Well, let me just remind you what z of s is. Z of s is always going to be u of x of s, y of s. And if I compute z dot of s, again, using the chain rule, this is going to be x dot times the partial derivative of u with respect to x plus y dot times the partial derivative of u with respect to y. Well, x dot is just a, so this is, I'm not writing the arguments here because there's not enough room. Y dot is b, partial derivative of u with respect to y. And by the PDE, this is just equal to, if I look at the sort of yellow PDE up here, this is just going to be CU plus D. So this is going to be equal to C of X of S, Y of S. And remember, U is Z of S. So this is going to be Z of S plus D of X of S, Y of S. And then Z of 0 is just going to be U of X naught, Y naught. So I want to make a couple of observations. This is a system of ordinary differential equations. The only independent variable is S, and the derivative of X is just given as a function of X and Y. The derivative of Y is given as a function of X and Y. But notice the derivative of Z is given as a function of X, Y, and Z. Okay, we've seen that. We saw that in the last example we did. We saw that Z was given as a function of Z. Z prime was equal to minus C. But this in general sort of this is the most general sort of linear framework that we can have. X is only going to be X dot is only going to be a function of X and Y. Y dot is only going to be a function of X and Y, but Z could be a function of X, Y, and Z. Next week, we're going to see what happens when X and Y, the X dot and Y dot can also be functions of Z. But for now, for linear equations, X dot is only a function of X and Y dot is only a function of X and Y, and Z is a function of X, Y, and Z. Okay, so that's going to be it for this video. I'll do this next example. I'll do this example in the next video.